Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. We stopped in the first part at this high-level abstraction. We said that we have to provide two functions, map and reduce, and there were some questions about whether the other steps are actually done automatically or not. We'll see. Okay. Any questions on that? Any questions on anything in the first part? Okay. Now we are ready to look into some more details about MapReduce framework. So here is MapReduce framework in one slide. We will assume that the input will be split somehow. Okay, so these splits will be done for us, and not exactly done for us, but we'll have first to define the input in pairs of keys and values. So every record will be a pair, key and value. And these keys and values can be complex by themselves, okay? But eventually, every record will be written or will be in that structure, key and value, okay? Dictionary, usually there's no repetition between the keys, right? But here it can be repeated. So it's not 100% perfect mapping, okay? Don't worry about how to call it. Just think that every record, it's not a dictionary. If that would be a definite answer, it's not a dictionary, okay? But it's just a key and value pair, because the key might be repeated across your records. There's no restriction here that the key here has to be unique. It can, there's no restriction that it has to appear once. It can appear in multiple records, okay? But the only restriction is that you will have to put it in that structure, key and value. Yes. Then put them all in what you call the value. Okay. It's up to you to define what the key and the value types are. Okay. But whenever we will just use K1 and V1 as the types. Okay. So here the types are K1. The type of the key is K1. And the type of the value here is V1, okay? And whenever we use the parentheses here, that means that it is just one pair, because the square bracket will mean a list of values. You will see the square bracket very soon. Type. Now, as we said, what is the idea of the map function? What does it do? It takes one record and produces something out of it. So every record here will be an input to the map function, which means that the map function will be executed over all records in parallel. Okay? So this is what we call the map phase. So in the map phase, the map function will be called for every record on all the machines that are assigned for that job. Okay, so theoretically, every record is completely independent in terms of processing from the other records. We'll relax this a bit later, okay, but you can think of it that way so far, that every record is completely independent and is completely independently processed from the others, which means we can run theoretically the map function on all the records in parallel. Okay, with me so far? Right. The map function will take one pair, which is the key and value of that record, which is the record itself, is key and value, and produce a list of keys and values, possibly in completely different types. That's why we said here K2 and V2. They can be of the same type, they can be different, it depends on what you want. And it can be 0 or more. So this list doesn't mean that it has to be at least one. No, it can be, it might decide the map function not to produce any output from that record, or one or more outputs. It depends on your application. Okay? So it can produce a list of keys and values also. They have to be keys and values. Okay? So that's the map phase. Now that will happen for every record. Some of the records will produce no output. Some of the records will produce many outputs. Okay? Right. The second phase in the framework called the shuffling phase. What happens in shuffling? What happens is that we will group all values by keys. What does that mean? All the values that are associated with the same key from the entire set of output, which we call the intermediate output, by the way, will be grouped together. So if specific key was generated as an intermediate output from multiple map functions with different values, what happens at the end of the shuffling phase is that all these values will be associated with that key. So we will get that key with a list of values that appeared with it in the intermediate output. That's why if you look here, you will see that now we have just one pair, one pair for each key, of course, which is of type K2. Remember what is K2? That's the type of the output, the intermediate output. The type of the key in the intermediate output, and a list of values. Why do we say here the list of values? Because that's the grouping. That's the meaning of the grouping. We'll group together, we'll find all the values that were produced in the map phase with that specific key. And we'll do that for all the keys that appear in the intermediate output. Where is the intermediate output? This is the output of the map phase. That's what we call the intermediate output. Okay? So this is a very well-defined operation. There is no need for the programmer to be involved here at all. It is very well-defined. Whatever the output of the map phase is, we will group the values in it by keys. Now, every key and associated list of values will be an input to the reduce function. So that's the piece of the intermediate output that will be processed by the reduce function. So the reduce function, the input to it is one key and a list of values. Where did we get this list of values? Where did we get this list of values? From these are the values that appear with that key in the intermediate output. That appear with that key here. Okay? Let me change this. So that's the intermediate output. What we have here is just the types. Okay? That doesn't mean that it's only one output, but these are the types. Okay, just to show you what will be the input and what will be the output. So the input here is one pair. The output here is a list of keys and values. Now the input to the shuffling is all of that output, intermediate output, and the output of the shuffling will be for every unique key, the list of its values. And this will be the input to the next stage, in which we will call the reduce function. So the reduce function now will take one key and list of values and produce whatever it wants to do with this pair, which can possibly be a completely different types, K3 and V3, and can be a list also. It can be 0, it can be 1, it can be 100, it depends on the data and the application. And eventually, this output will be written to disk, will be the final output. Okay? So this is called this is the input. This is called the intermediate output. The intermediate output through the shuffling phase is grouped, okay? And every single key will be processed by one reduce function. What is the role of the programmer here? Write the map function, which will be called on each record, and write the reduce function, which will be called for each unique key in the intermediate output. Might look complicated, right? We need an example, for sure. We need to see how we can do something useful out of this. Okay? So here is, usually when you learn a new programming language, what is the first program that you write? Hello World, right? So in MapReduce, it's not hello world, it's word count. So what is word count? That's the classical example that is always used. Yes, so you have a collection of documents, textual documents, and you want to count how many times each word will appear in the entire set of documents. So for this toy example that I think if you look at the words here, you will find out when I actually designed for the first time. You can see, for example, the word Clinton here appeared 1, 2, 3, 4. So eventually, the output of that job will be for Clinton 4. So we'll get Clinton 4. Okay. Trump 2. Okay. So we need to figure out how we can use MapReduce to do this. Okay. So you understand now what is the input and what's the output? So the input is maybe document ID. We have to have the input as key and value, right? So what are the key and value here? Document name or whatever, or title, or usually it's an ID. Okay, it can be a number, URL, whatever, something that will describe or will identify the document. And what is the value? The document itself, the text. No, not words yet. The text. Okay? It might be one string. You need to divide it. Okay, so that's the key and that's the value. And how about the key and value? Remember in the previous slide, the output also has to be in terms of keys and values. What would be the keys, the key type and the value type in this case? In word count, yes? Word and a number, right? Integer. Okay, type. Now we need to think how to do, what will be the map function and what will be the reduce function. So you need to think that way. You need to think, how can we process every record here independently to get something out of it that can eventually be combined to get the final output. That's the first point where you need to change your mentality now about sequential algorithm. Okay? Sequential programming. It's no more sequential. It is done in parallel. The processing of the map function is run in parallel. So you need to think what you will do only with one record. Okay? And then the shuffling will do something for you, and then the reduce will produce the final output. Any ideas how we can do that? Right. Since it's a first example, let me go through it, okay, and then we will discuss it together. Right. What can we do with the map with the document now? We have the map function has a key and value. Yes. Let's be very simple. Let's be very simple. What can we produce? Huh?
It's an input for the map.
Yes, of course. The input to the map function is the identifier of the document, like ABC here, and the text of the document. Okay? Should we do anything with the identifier? With the key? Should we care about it?
Well, we should check whether it repeats itself, right?
Why should we care? What we want eventually is the count of each word. Do we care about the ID of the document?
No, but obviously, the task is
Okay, I got your point. You don't need to worry about this detail. I think you are thinking whether we might process the same document twice or something like that. Okay, no, this is done by the framework. The framework keeps track of that. Okay, it guarantees that no one record will be processed more than once. That's one thing that will ease your mind from that. Okay, so things that you might always think about in traditional programming, you need to free your mind from and put some other things in your mind when you think about that. So what can we do with the text now? So I think we all agree that we don't care about the key. It will be just ignored. That's fine. Okay, it happens. So the key will be just ignored in the map function. But what can the map function do out of the text to help finding eventually the count. Yani think about what we actually need to do even on paper. If I give you one document at a time, what will you get from that document so that eventually you will aggregate whatever you will get to get the final output?
We can split it to words.
Sorry?
We can split the document into words. Different words.
We split the document into words, yes. Then, so of course we have to do that because we eventually want to count the words, right? So we need to get the words first. The text is just one string. We'll divide it, and we don't care about how to divide it. Yani, just assume that there is a way to divide it. So we'll get now the words. We get a list of words. Okay, that's what you said, Anila, right?
Yes.
Okay. Now, what is the next? What else? We didn't say what we will produce yet. Okay. So, since we want to count, why do you need to compare it? Okay, but that's eventually, that's at the end, right? But what we can do with the words now, at least we know that this word appeared once, right? Right? Because we see the words. Yani, if, let's say, I think I need to use this now. Let's say that we have here Clinton. We have here Clinton, Trump, and Clinton again, right? Every occurrence of a word indicates that this word appeared once. Now, right? So we can say, we can produce for each word. Remember that we have to produce key and value also, right? The output has to be always in key and value, but list of them, but they have to be of the same type. And all of the output records have to be of the same type, but these two types don't have to be of the same type of the input. Okay? So, since the occurrence of every word indicates that this is a count of one, it appeared once, we can produce something like this. We can produce Clinton, okay, and 1. Trump, 1. Clinton, 1. Right? So that will be an output from the map function. There is no notion of rows here. There are records. Okay? So yes, of course, each record is separate because we have key and value. So that will be the output from the map function. Now, why is that useful? Yes, because remember, what happens in the shuffling? The shuffling will combine all of the intermediate output. So let me now erase this and show you, now what will happen with the map function if we do that. So the first one will produce Clinton 1, Trump 1, Clinton 1, and here is also the same output for the other documents. Now, what will happen in the shuffling? Can you tell me? I think with what we discussed earlier, you should know exactly what will be the output of the shuffling phase. We will group by keys. So every single key here will have the associated values with it. So Trump, what's going on here? Okay, so we have Clinton here, we have Clinton here, we have Clinton here, we have Clinton here. All of these will be grouped. So we'll have Clinton, not 4. Why is it 4? That's a big difference. There is no computations that is done in shuffling, and this is very important to remember. Shuffling doesn't change the data, doesn't do any computations, just grouping. Yes, key and values, yes. So it's not 4, it's 4 ones. There's a difference between the number 4 and 4 ones. So actually it will be something like this. 1, 1, 1, 1. Yes, sure.
Because of the shuffle itself, that's why we have this waste of the memory that we assign the value in this kind of operation. If we will be doing the reduce immediately, there will be no need.
We'll get to that. We'll get to that. Okay? But that's how the framework works. It takes whatever the intermediate output and group it by key. So what else? Do we have also only Clinton? No, we have also Trump here. We also have Trump here. Okay, so we have also Trump and what would be the values? 1, 1, because we have 2 ones for Trump. How about what else? Sanders? So let me do it that way. Sanders just once. So it should be just 1 like that? No, it's a list, but it's a list that has just 1 element. And Donald. So how can I do this one? Okay, maybe something like this. So Donald and what? Just 1. So that's now the output of the shuffling phase. Every pair, this is a pair by the way. This one is just 1 pair. Key and the value is just a list. But it is just 1 pair. Okay? Now this pair will be input to the reduce function. Every single pair here will be assigned to 1 reducer. Okay? It will be called by the reduce as an input to the reduce function. Okay? Now what should the reduce function do? It will just sum over the ones, right? And that will be the count for the word. Yes? Mm-hmm. Yeah, we can do that. We can do that, but I just want it to be just simple. Yeah, it can, of course, you can do that. You can do that. But this is much simpler, right? Yeah, I don't need to count within the document. I will leave MapReduce do the work for me.
You don't need to come back to actually confirm that the word already appeared. You just go word by word.
Exactly. You will not need to do this checking. Okay. We'll talk about that very soon. Keep that in mind. But at least you understand this one, right? Yes.
Doing this, so it will take more time than doing the count.
We'll get to that, wallahi. Okay. But let me make sure that you understand how this works first, and we'll talk about these issues. Okay. So let me erase this and show you the entire thing now. Okay. So this is the shuffling for all occurrences of Clinton. They will be grouped, and you will see that we have these ones, and for the others also. Then this will be the input to the reduce function. Now, what should be the output, by the way? Clinton 4. So this is the key value. How many records for each input we will produce? 1. We don't need more than 1 here. Okay. So it will be Clinton 4, Trump 2, Sanders 1, and Donald 1. Yes. 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 Each key will be an input to the reduce function, separate from the others. What's your question? They will be called more than once. Okay? But for your understanding now, it's important to know that these are independent. Okay? Whether they will run on the same machine or not, we don't care about that now. Okay? But what I care about here is that every key and the associated values will be an input to the reduce function. Okay, independent from the others. Yes. Okay, we'll get to that. We'll get to that. Okay, but for now, you don't control how many mappers. It's just a quick answer, but we'll discuss that later. You don't control how many mappers, but you control how many reducers. And you can define, you say, I want just 5 reducers. Because actually, when we talk about the details, you'll see that there will be one output file per reducer. Okay, and I don't want now to get into the word reducer. You hear me say reducer, not reduce, right? Just think about this abstraction for now. Okay, that there is a map function. The map function is called in parallel on separate records. Also, the reduce function will be called in parallel on separate grouped keys and values. Yes, you have a question? I think you had a question before, right? Yes.
You said that reduce is actually map is the input is pair.
Yes.
But reduce is list, right?
Is a pair also, but key, but the value is a list of is a list. Yes. For the reduce function. Yes. 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 Is not related to. Of course, it is related. Of course, it is related, and it's also related to the size of the data. Okay.
We have to define that.
You can give a hint. We'll talk about these details later. Okay. You can give a hint, but you don't control it. What control the number of mappers is the framework itself. You control the number of reducers. You can say, I want 10, it will be 10. Okay. Any other questions? You need now to think of, or you need to understand how the framework works so that you can solve your problems using that model. Okay, so that model in an easy or in a simple way, it processes each record independently in parallel, produce some partial results. These partial results, we call it intermediate output. Then the shuffling phase will group these partial results together. For each key, we will group the values. And then looking at this key and this list of values, you produce the final output for that key. Okay? So now knowing that model, you need to map it to your actual problem. You need to think how you can use it to solve your problem. Okay? Any questions? Should I go back to this slide now? I think maybe you understand it more now. Any questions on this? Okay, here is a pseudocode for it. So as you see, we need to define just... No problem. Should I go back? Yes.
Just again,
to the previous slide or this slide? Previous one. Okay.
So when I ask, I understand that shuffle has a unique key and the list for values. But the reduce is list of keys and values according to this representation.
The reduce takes each reduce function gets an input that is one key and list of values.
So basically it should be represented as shuffle is represented not as a list. Because now when you look at it, it's a list, right? K3 and V3.
K3 and V, that's the output of it. The output is a list of things. Yes, it's 0 or more records. That's the output.
That's what I was asking. So when you told me one key and
oh no, that's the input.
That's an input.
Yeah. Maybe I misunderstood your question. No. The input is just one pair, but the output can be 0 or more. And they don't even need to be of the same type as you see here. It's K3 and V3 generally. Of course, they can be, but generally they might not be. Okay? Please ask me questions here and as you wish. This is the core concept of MapReduce. It's very simple. It's very simple. Yes. Yes, it can be. I said 0 or more. This is for this application. It is just you just need one, but for other applications you might need more. So it's general. You can produce. Yani the framework allows you to produce 0 or more. It's up to you. No. Okay. I see your point. I see where you are confused. Don't bother yourself now with how many reducers we have and how many keys we will have out of the shuffling. Okay? Let's assume for now, just to ease your life. Okay? Let's assume that we have a number of mappers like the number of records, the input records, and we have a number of reducers like the number of the output of the shuffling. Just to, خلاص, يعني that's fixed for us. Okay. Later we'll know how this is that this can be relaxed, but for now it's enough for us to understand it that way. Okay. Ask me. It's what? It's clear. It's very simple. It is actually simple, and it's not that hard. But you need to really get used to or practice how you can use it to solve your problem. Okay, and not everything can be done this way. One thing, by the way, that maybe I didn't mention yet, is that the input always is on disk. The input always resides on disk. The data is on disk. Okay, and it is read to be processed by the mapper, by the map function. And also the output is written to disk. So the output doesn't reside in memory. Okay? That means that if you have a pipeline, you can of course have a pipeline of jobs, by the way. And you can say, okay, my problem will not be solved in one MapReduce job. This is called the one job, by the way. And this is the running of one job. You can design your process into 2 jobs. One job will produce that output, and then this output will be an input to the second job. Okay? But you have to understand that every MapReduce job will write its output to disk, whether you will use it for another one or not. It doesn't know that you will use it for another one. Okay? So it will always be written to disk and then read from disk if you need it for the next job. Okay? Did you get that? So you don't have always to solve your problem in one MapReduce job. Okay? Maybe it's more complicated than that. So you need multiple, and that's actually this is the norm.
So you mean the output of this job could be the input of the other one?
Exactly. Yes. By the way, if you notice, it is ready for that. Why is it ready for that? Because the output here is what? And key value pairs. The output here is key value pairs, which is ready as structured to be an input for another job. And now I can take these numbers, counts. Let's say that I got the word counts. Maybe the next step is to do something with these counts. I don't know. Maybe doing some statistics out of these, something like that. Okay.
Each job has the same structure. Map, shuffling.
Of course, خلاص, this is a replication of this of that structure. Each job is the definition of the job.
And the role of shuffling always grouping, or it may have other functions.
What do you think?
Because what I understood from shuffling, is some mixing, random.
Okay. Maybe you are confused with the word. Okay, but that doesn't mean that there is something random here. It is very well defined, as I said. It is just grouping keys by values. That's it. It's always doing that way. It doesn't, yani, next day when you woke up, it will not do anything new. It will be the same shuffling. It will be always,
The shuffling.
it will always be grouping, yes. Didn't I do it that way here?
Yes.
It is defined that way, and it will always be that way unless they change the model. But it is like that. So you don't need to provide code because there is code already within MapReduce framework that does this for you. You don't need to. But by the way, but you control the semantics of it. Yani by defining the types, by defining the type of the map function and the type of the type of the output of the map function, and actually it's just the type of the output of the map function that will define how this will work. But the actual thing that is done is already implemented for you, and it will be done for you. You don't need to provide anything for it.
That's why I asked when our colleague asked about that step number 3. That's why I asked if it's really that you don't have to influence it.
But we don't interfere within it. Yeah. Yeah, but we kind of control it.
Because there's no way for it to know the types in the sense that you.
Well, we have to provide the types, of course. Yes.
So there is interaction between map and reduce.
Just in the types.
Yeah.
But other than that, it is well defined. It is like a function that is there. It will be called for you. After you are done with the map, theoretically, after you are done with the map function, it will be done for you. Okay? More questions? Right. This is the pseudocode. We have, as I said, we need to just write two functions. Here the map takes the document ID and the text, and for each word in the text, of course, here we assume that we have a way to divide the words. We will emit, this is the function emit is to provide the output of the map function. So we'll emit W and 1, the word and the number 1. And the reduce will be, will take the word and will take an iterator. I think you are familiar with the iterator in programming, right? Iterator is going through the list of, iterates over the list of values. So with that iterator, you go through all the V's in counts, and you sum over all the values, and you emit eventually the word with that sum. So how many lines of code to do this? Very few. How much data we will process? We don't care. This will work on 2 documents as it will work on millions of documents or billions of documents. We don't care. As programmers, we don't care. It's the same code that we run on to process whatever size of data that you have. Of course, you have to provide where the data is, and there are some configurations, of course, okay? But these are straightforward things, and you have to define the types. But this is the main thing that you need to focus to write, to design. What the map function will do and what the reduce function will do. Okay? You don't ask any questions. I'm worried. Huh? You're fine. Okay. Asking questions is also good. Any question about this? I think this is straightforward, right?
Straightforward, but you said it
Is producing the output. Yeah.
what's W there?
Which W? Here?
In the map.
W is each word in the text.
Each word in the text.
Yeah, assuming that this is pseudocode, of course, right? So assume that you have a process that will divide the text into words here.
Okay.
Yeah. This is specific to this task, yeah. So that's why we abstracted here. Okay. Any other questions? Okay. Type. Now the question is, can we do it more efficiently? I think you gave some hints already. Some of you were worried about this already before getting even into the end of the process. How can we do that more efficiently? Yes, instead of producing each word with 1, we can locally count. And for example here, instead of producing Clinton 1 twice, instead of producing 2 records for Clinton, we can produce 1 record, which will be in this case Clinton 2.
In the end, the goal is efficiency and everything. If you have very large text with a lot of words doing Right.
That's my question now. What will save? What will be saved here? Yani, why is that? Why is that more efficient? No. I mean the new idea, okay, which is locally aggregating the counts for the words within one document before we move forward. Okay. Then now the number, huh?
Memory stuff is going to be, utilized less than when you write it this way.
Actually, here we don't need any memory. Here, with the new efficiency trick, we need memory.
No, I know, that's what I'm saying. In this case,
Which case? Because we okay, this simple one.
yeah, it's a waste of memory.
Memory? No, that's exactly what I'm saying. It's not waste of memory. Okay, so stay with me a bit. Okay, what are we wasting here? In this solution, we are producing 3 records from this first map function, right? In the new one, it will be 2. Right. Forget about what is going on in the map function itself. Okay, we'll get to that. But now, in terms of output, we have 3 in the first solution and 2 in the second solution. Is that a big deal? Huh? Is it a big deal?
Based on the current storage devices.
Why is it a big deal? Why will that make a difference in terms of the time that is needed to do the job? We are not storing this in memory. We are storing. Okay, so let me tell you something. The intermediate output is written to disk, not in memory. The intermediate output is written locally on the machines that will do the mapping. But if you think about this shuffling, what is actually going on in this shuffling? So there is lots of moving data around the network here. This is the most expensive part of MapReduce. That's the most that's the bottleneck actually. In many cases, in most of the cases, the bottleneck is the shuffling. If you do the shuffling efficiently, you are in a good shape. So the size of the intermediate output, all of this data will move around the network because here we are actually, for example, here let's take this example. Look at exactly these arrows. We are moving this record and that record and that record and that record to one machine so that this will be an input to a reduce function that will run on that machine. So that's moving the data across the network. If we minimize this, we will reduce what? Reduce time. Of course, the word reduce here is not the reduce function. Okay, we will minimize the time. We'll make the time of the shuffling less. Okay, which means the time overall will be less. Okay, and we'll free, of course, the network for other things. We'll get to that. Okay. Step.
Processing to data. Obviously, there should be some mechanism.
Okay. We'll get to that. Remind me again. Okay. But did you get that point? That the shuffling is done across the network. This is very important point to remember. Okay. And it's very expensive. That's why you need to be very careful when you design your job, when you design your map and reduce function. Because whatever will the map function produce as an intermediate output will be shuffled across the network. So you need to minimize that output as much as you can. Okay? So that you don't move lots of data across the network. So back to this example, if we manage it instead of having Clinton 1, and move it to across the network, we can have Clinton 2 only. So we do kind of local aggregation. Okay, so we remove some redundancy. Still, of course, Clinton across different maps will not be aggregated because they are independent, right? Remember, with this trick, we can aggregate these two. We can, sorry, what happened? Where are we? I think we are here. We can aggregate these two, this Clinton and this Clinton. Can we aggregate these two with this one? No, because they can run on different machines. So we cannot do that. So we cannot aggregate everything, of course. But we can do some local aggregations that will save us some time in shuffling. Okay? So that will make, of course, will that change the final output? It won't change the final output. The final output will be the same. So it's not about correctness here. Okay? It will be the same thing, but you need to be a bit careful about the output, the intermediate output. You don't need to produce redundant data that you can locally aggregate. Now, what is the side effect of that? Now, coming to your comment earlier about memory. How much memory we need in this simple case when we produce just one, with every word, just one? Do we need any more memory than just the variables that we have? We don't need to keep track of anything. Every word, just produce one. Yes.
As far as I know, on the stuff, this every class is going to be saved on the stuff. So basically,
Which
for example,
yeah.
when you're iterating to the text, right?
This one, this step? Yes.
You're doing math.
Uh-huh.
That's what we're talking about.
Uh-huh.
So when you're iterating through the text,
Uh-huh.
for example, in the first example, you're Clinton to Clinton because it has separate value. Will be saved 2 times.
Oh, no. We will not save. Okay, this is a good point. We don't, and I think I just said it. Maybe you didn't notice that. The output of the math function is not kept in memory. It's written to disk. Not directly. It's buffered in memory.
That's what I'm saying. I'm talking about
Okay.
memory stuff.
Okay. So we'll talk about these details later. Yes, it's buffered in memory first. Yes.
So you're going to be affected.
Yes, but I was not talking about the memory controlled by the framework. I'm talking about the memory within your code that is needed for your code. Now, if we do this local aggregation, we need something like a dictionary, right? Like a map in Java, like a hash map, or so that you can keep track of each word and its count, right? And that needs memory. So that's what I meant, that you might need a bit of more memory. But of course, the documents here are not that much, so that you worry much about this memory that is needed. The efficiency that we will get out of doing this local aggregation is much more important than the memory that we will need more. Okay. Any questions on this? Okay. Now, can we compute number of documents per word? Can we change this instead of counting the number of times that the word appeared overall? No, here I want to compute the number of documents per word, not total occurrences. For example, let's get back here. Here, Clinton, how many times Clinton appeared? 1, 2, 3, 4, right? But how many documents? Huh? Yes, how many documents had Clinton? 3. Okay, so that's different. Okay, you got now the difference? How can we change this to compute the number of documents instead of total occurrences? So what should we change here? What should we change here? Yes, in that code. This code is word count, right? I want to change it to get the number of documents instead of just number of occurrences for each word. يعني eventually I need Clinton 3, Trump أعتقد was 2, something like that, right? Trump was 2. Okay, I'm listening.
No, I mean, it's a little bit hard, you jump back, you can go back to the code.
Okay, here's the code. Take your time.
So, in the map, we will be looking only for word ones that appear in the document in order for that document to be counted.
Very good. Yes. Yes. How can we do that?
We will not iterate for word for all
Yes.
text. We will just first time when we hit
So tell me the semantics. Yani, what should we do in the map function? Yes? Yes. So it's not for every occurrence of a word, only for the unique words, we need to produce this word and one. Because that means that this word appeared in one document now. Not appeared once generally, no, appeared in one document. Did you get the idea? Did you get the idea? Okay, it's clear. It's clear that you did it. Okay. Did you understand this one? When we said that, let's make it more efficient. Okay, what would we do to do that? We need to get some way to check if that word appeared before or not, right? So that we can aggregate the count for it. Here we'll do exactly the same thing, except that we will not aggregate the count. We'll just indicate that it appeared. Just appeared before. Okay? So that we can keep track of only the unique words. So instead of producing Clinton 1, Trump 1, Clinton 1, we'll not produce that one. Because we know that the only unique words in that document is Clinton and Trump. So we'll only produce these two records from here. Okay? Here, it will be the same, right? We will not change anything. Here, we will not only also change anything. Okay? So now, that number doesn't indicate that it appeared once. It now indicates it appeared in one document. Okay? And then shuffling will aggregate these ones, and then the reduce will sum it. You have a question? Is it clear? Okay. Because I see a smile. What does that smile mean? It's clear or not? Okay. Another smile. That's the point in time that you need to start changing your mind. Okay? To think of how to use that model to solve your problem. But you need to keep the model in your mind. You need to understand how the model works. Okay? Each record is processed by a map function. The map function will produce some intermediate output. This intermediate output will be grouped and will be passed to the reduce function. So you have to think, one way of thinking about it is to think backwards. You start with what you want to produce, because you know that this will be produced by the reduce function. There's no way other than that. Okay? And then you see how you can get to this output. And then back to the map function. Of course, you have actually both. You know what is the input and what's the output, so you can actually go both ways. You can start with the backward, thinking about how to get the output, and you also know from the input what is the structure of the input. Okay?
actually,
It needs practice, for sure. Yes.
You said data center is computer, to think of it that way. Then you apply this, what we mentioned, functional programming, it's map and fold actually, with the additional shuffling that's done by framework, that's it.
Yes.
I mean,
Yes.
it's not-
You don't need to worry about anything. You don't need to see the data center. No, that's what I meant by the data center is the computer. You don't need to see the data center. You don't care. All of this will happen for you, but just focus, please, on solving your problem. Excel in that, and everything else will be done for you. Okay. So, as I just mentioned, framework handles everything else. So you just need to define the map and reduce function, and that's it. For now, at least, that's required.
So this fundamental thing did not change in MapReduce version 2.
To my knowledge, no. Yes.
So is there any other than MapReduce?
Any what?
Another technology?
Of course. This is the parent, but not so many children now.
I hear there's other.
Yeah, of course. We will study some of them, but we'll spend some good time in that because that's the core. Okay, if you understand this very well, the others will be really easy. So we said here the framework handles everything else. What is everything else? Handles scheduling, which means which worker will be assigned to which part of the data, whether it's map or reduce tasks. It handles data distribution. It moves the processes to data, which means it knows where the data is and thus assign that part of the data to the processor that is at that machine. It handles synchronizations between the workers. It handles errors and faults. If one machine failed, then the framework will be responsible of calling another or using another worker to do the job that was supposed to be done. And all of that, of course, is supported, as inshallah we will, I hope that we will cover it, by a distributed file system. So MapReduce is actually very attached to Google file system. There is a distributed file system that is called GFS, or Google file system. So we'll have to also to understand how this file system works. Here's another example. So how many examples we went through so far? 3. Who said 3? 2 variations of the first one, which is word count, and then document count was the second one. That's the third one. So what do we mean by indexing? I'm not assuming that you know what indexing is, so let me introduce it. So you have a collection of documents like this one, and eventually you want to get what we call an inverted index. What is an inverted index? For each term, you will say which documents in which this term appeared. So for example here, I want Clinton, and then you tell me that Clinton appeared in document A twice, document B once, document C once, and so on for the other terms, for the other words. Okay, so this is a bit different than the 2 examples before. Not very different, but it is different. Okay, so the input is the same, by the way. The input still is document ID and text. Okay, but now the output is each word and what we call a posting list. Okay, forget about the terminology now. It's just the list of documents in which this word appeared, along with the number of times this word appeared in that document. So here, for example, Sanders appeared just in one document, which is B. It appeared once in that document. So is the definition of the problem clear? Is it clear what is the input and what's the output? Okay, now I'll give you a couple of minutes. Think how we can use MapReduce to do this. How can we produce this output from this input? When I tell me how MapReduce can work, you have to define to me how many things? You define to me the map function and the reduce function. You need to tell me what is this the types for each, what the map function will do, and you define also the types, the input types and the output types for the map function and the reduce function. Of course, I think you notice that once you define the output types of the map function, it's by default you define the input to the reducer, right? So you don't need to do that. You just need also to define the output of the reduce function. Okay, yes. Maybe because you know already. Reem? Yes. Go ahead.
Map function will have input of, it's very similar to the board content we did
Okay.
before, with the notion that the output of the map function will be document and countable as a value and key.
طب يعني give me an example here. Let's say that now, so you said that this, the input will be the same, right? So the map function will take one document ID, okay, very good. So that will be an input to one map function. What will be the output?
The output of the function will be the number of the word.
What is the key type and what's the value type?
Key is the word and the output.
And the value is?
And the value is number of because output is a list, so it can be multiple values, right?
It's a list of pairs.
Yes.
Yes, but I'm talking now about the type, just the type, just to know it. So you said that it will be, the key will be a word and the value will be what?
It will be number of occurrences.
Okay, so let's call it frequency. Okay, so the word and the frequency in that document. Okay, so you assume that here you will, how many records you will get, you will emit here? 2, right? So one for Clinton and one for Trump, right? So we'll produce here Clinton and 2. Okay. And Trump 1. Okay. So that's what you suggest. So you will get these 2 records out of the map function here.
That's very similar to the previous.
This is very similar to what to the efficient solution of the previous one. And of course, this is done everywhere. Now, when we shuffle, what will happen?
When we shuffle, we will just get the total number, but we need the
No, shuffling doesn't do any computation.
when we shuffle, we will
Yes.
shuffle the document.
So we'll get Clinton and what? 2 for this one, 1 for this one, and 1 for this one. Okay. How can you get from this to this?
We need to pass in which document we have found.
Okay. You didn't tell me that. Why do you think it's assumed? You told me. No. You told me that it's a word and the frequency. You didn't tell me anything about document ID. Okay, so we should change something here? Which is?
You know what? You're looking at me, and now I'm lost. I know what I want to say, but I don't want to.
Okay, remember that the value or the key can be complex. Doesn't have to be just one.
That's what I wanted to say. I mean, what I meant in shuffle. In shuffle, you get one key and then list of
The values, yes.
So I meant,
Whatever values that you emitted here,
yes.
whether they are simple or primitive or complex. Yes.
So what would reach shuffle would
Yes.
be key, which is word, and then list of values, which is document, and number of the.
We don't call it, it's a tuple. It's not a list of values.
Yes.
It's just one value, which is a tuple. Okay, so because here, what you did here is that you lost the document ID. You will never get it back. Did you see the problem here? And if we do that, we are lost the document ID. We will never get this anymore. So we have to keep it. Yes, so we'll have to, instead of only producing the frequency, we'll have to produce also the doc ID. So this will be just a tuple. Doc ID and the frequency. So let me change this. So that will be Clinton and what, Karan? A2. And this one? A1. Wait. Is that clear? Okay. And we do the same for the others. Now we don't have just two, we have A2. We have B1 and we have C1. Okay? What will the reduce do then? It takes the input and produces it as an output. Doesn't do anything here. Because the list is already ready for us. Unless you need to sort it or somehow. But the list is already ready. You don't need to do anything in the list. Yes?
So what's the role of shuffling? I didn't get it.
Okay, so we'll show it now. Okay, so let's assume that these are the documents. Okay, here is what so this is another version. Okay, that's the version that is similar to the simpler version we started with in word count. So we don't do local aggregation here. Okay, so what we do here is to produce for each word the ID with it. So that's simpler than your solution. So here, the key, so this is the key. So the key is a word, and the value is the document ID. This is just a simple tool. Shuffle will now group Clinton with all of the values, even if it's repeated. Then reduce will remove the duplicates. Not only remove the duplicates, but also will do what? What is the output that we want to do to get here? Count. So it counts the number of repetitions for each document also. Okay? So it will produce something like this. Each document with the number. Okay? Is that clear? Clear? And use is, of course, a bit more efficient because we don't need to produce multiple records here, but it's a bit complex. It's a bit complex.
Maybe this one is more efficient because your side.
We did some work on the map side more, but remember, but it will save us in shuffling, and saving in shuffling is a big thing because that's done over the network. What the processing that you're talking about is done locally, but this shuffling is done over the network. So you need to really optimize the amount of data that will be shuffled. Yes, yeah.
So does that mean using shuffling is optional? It's not mandatory.
Did I say that?
Because now in his approach for efficiency wise,
Uh-huh.
I'm counting in the mapping, right?
Yes.
Then what's the role of shuffling in this case?
Shuffling is always doing the same thing. It's grouping the keys by values. Whatever keys you are producing will be grouped. Whatever values you are producing will be grouped by keys. Whatever you do.
The grouping in this case it will be one.
Exactly. It's not 111. It's, I think we still have, yeah. It will be grouping whatever you will produce from all the mappers.
I mean one in terms
But-
of
but-
key and value. Because I already done the
Yes, exactly. Yes. But shuffling doesn't care about that, doesn't understand. It doesn't do any computations. You need to keep that in mind. Shuffling doesn't do any computations. It does, you know, in database group by does anything. Actually, it does some, we can do the summation or something. But forget about what you do after you group. The actual grouping function is just grouping. It doesn't do anything. It just gather the values of the same key. That's it.
So I can do computation during memory, right?
You can do computations in map, and you can do the computation also in reduce. You have these two functions. Do whatever you want to solve your problem. Okay? The code, there's no restriction except in the types. Okay? All the output records have to be of the same type. And you understand that this type will define the input to the reduce function. Okay? It's keeping that in mind. Yes. Yes, it's group by always is the same definition since the beginning of databases. Okay? It does grouping the values by keys. Of course, in data, I think in group by command in SQL, you can also define what you will do with the list of values. This is kind of reduce here. And what you add to the group by in SQL to do the sum or whatever is like defining what you will do in the reduce here. But shuffling here is just the core grouping functionality. It doesn't do any computations. Okay? So here is the solution. Any questions about that? Yes. From what we get, the last reduce function. This one? This is, I think, this is a mistake. This is a typo. It shouldn't be Barak. It should be what? Donald. Yeah. Yeah. The problem of teaching the course multiple times and changing your mind about the examples. Yes, the first version had Barack Obama and the second version has Trump. So yes, that's a mistake. So that should be actually Donald. Any other questions? Clinton should be what? Oh, no. I'm saying, I'm talking about this example. In this example, this is a mistake. But having Clinton is not a mistake generally. Any other questions? Okay, good. Fine. We mentioned that the framework does everything else, right? And that you only have to provide the map and the reduce one. That was not exactly right. Okay. So you can, but optionally provide other things. What are these other things? You can also specify two other functions, but you don't have to. They are options. The first one is called partition, and the other one is called combine. Right. What does partition do? Partition tells the framework how you distribute the keys over the reducer. Yani, let's look at here. Who says that this reduce will take Clinton, and this reduce function will take Trump, and this reduce function will take Sanders, and this reduce function will take Donald? Your earlier question, what if we have, what if we have only two reducers, and we have 4 keys? Which keys will go to which reducer? Okay, there is a default way of doing it that MapReduce will do for you if you didn't tell it how to do it. But you have also the option to provide this partition function. So this partition function takes a key, which is the key of the intermediate output, and the number of partitions as a parameter, and produce a number, which is the number of reducers that will be assigned to that key. Okay? Usually we use a simple hash function. We take the key and hash it to get a value, and then we take the mod with the number of reducers to assign it to one of them. And this will kind of fairly distribute the keys over the reducers. Did you get that? Let's say that we have 100 keys, but we only have 7 reducers. Okay? We'll hash the key to a value, to a specific, of course, the hash function will produce a number, right? So it's like mapping each key, whatever the type of the key is, to a number. Now, that number, we take the mod with the number of reducers. So let's say that one of the key got the number 13, and we have 7 reducers. So this will be assigned to the reducer number 6, because mod 13, mod 7 is 6. Okay? So it will always be assigned to one of the number of reducers from 0 to n minus 1. Okay?
And it's always working in this way? Or
No, it's not always. This is usually what we do to balance the load of at least the keys randomly across the reducers. Okay? But you can do whatever you want. You can think of other ways of doing it depending on what you want to do. Okay? Is that clear? So you can provide this function. Also, you can provide another function called combine. What does this combine do? Remember the local aggregation that we talked about? That we can do within the map function some local aggregation of the words so that we don't produce duplicate keys in the intermediate output. The combine function does something similar to that. It takes first it runs at the end of each, at the map site. Okay, so it runs locally on the output of one mapper. Okay, and does something like the reduce, but it's mini reducer. It does whatever aggregation it can do on the map site before moving the data across the network in the shuffling. Okay, so let's look at the signature first to understand it. It takes a key and a list of values. Where did we get this key and the list of values? Remember that we had something like this, right? We have multiple map functions, and each map function produces some records, right? One thing that you also need to understand is that although initially I told you that imagine that we have the number of mappers to be equal to the number of the records, right? Is that feasible? Huh? And is that realistic?
no.
Why not? Who said no? Why not? Huh? Because it's big data, right? We have maybe millions or billions of records. I don't think we will have millions or billions of processors, right? At least for now. So it's realistic to know that it's always the case in most, if not all the applications, that the number of workers will be less than the number of records. Which means that you will have to process multiple records in one machine, in one node, right? So that's intuitive, right? Logical. So that means that on one node, the map function will be called on multiple records, but they are still on one machine. So the combine function actually will work on the intermediate output of intermediate output of those calls on one machine. And now imagine that these two maps, map calls, so these are map calls, right? We didn't say where they are, but let's assume that these two map function actually executed on the same machine. It can happen, right? We just said that the number of workers will be less than the number of records, okay? So that means that this output and this output are produced on the same machine. So why don't we do some aggregation now, locally? So we can aggregate these two before doing the shuffling. So this is now not aggregation, local aggregation inside the map function itself as we did before. It's across different map calls, but on the same machine. So it's not expensive. We will not move any data across the network. It will just work on the data that is produced by the map function called on the same machine multiple times on different records. Yes?
So, now in the real world, Hadoop.
This is the real world.
No, I'm saying in the real application, this is an example.
Yeah.
I've seen some large implementations with not many physical nodes or data nodes in Hadoop.
Yes.
So, like very large data storage, a lot of data stored on, let's say, 6 data nodes.
Yes.
So it makes much more sense to do combine.
Of course, yes.
Because processing power is there.
Yes.
And moving of data is not that much because it can happen that everything that is done on one data node. Because the way HDFS works is
big file, big blocks. Yes.
It says at least they are in implementation with 6 items. So basically, combine should be kind of core requirement for.
Exactly. Yes. Combine is very useful. That's what you want to say. Yes. Combine is very critical. And especially when the data is huge. Okay? Because if every map function will produce something and it will move across the network, that will take a lot of time. So combine is an optimization that is done locally. Okay? But it's optional.
That's right.
You can.
Optional, and I'm thinking now of my environment.
It depends on how much data you have, how many machines you have. Okay? So it's optional. You don't have to provide it. And even beyond that, even in Hadoop, it's not guaranteed even if you provided that it will be called. It depends on the runtime environment. Okay? But you can provide it, of course, and it can be used if possible.
This is important information.
Yes.
It's not mandatory for Hadoop to use it to decide.
Even if you provide it. Yes.
This is the most important information.
Yes.
That's why it's optional.
Yeah, but I want to make sure that you understand first how it works, because I don't think we finished this discussion yet. Right? You understand how combine works? Yes, here, but I don't see the same yes here. Yes? Not very yes. Okay, so we didn't finish it yet. So again, combine. Combine will take key and a list of values. How did we get this list of values? From the same node. Okay, so this is like that a small group by happened locally. A small shuffling happens locally before the actual shuffling across the network. Okay, so the values for the same key was grouped and then passed to your combine function. That's why we call it mini reducer, a small reducer, because it looks like a reducer. It will take a key and a list of values and produce a key and value, list of keys and values. But with one one clear difference with the reducer. When we talked about the reducer, we said we can produce the key and value pairs in different types than the input, right? We said that you are free to do anything. But this one, you cannot. Why? Because it might not run. It has to actually produce the same output that was supposed to be for the shuffling. So you cannot change here. It has to be key and value of the same type like the input to it. But aggregated, that's the main thing. Did you get that point? It's very important. Yes. That's a big objective. You say it, yeah, it's like, no, it's big. It's a big thing, of course. It's a big thing. Combine makes a big difference. If you do it in the right way, of course. Because it saves you lots of intermediate output that will be combined, reduced later. And you have to align the logic of the reduced function with the combined function. That's why it's called mini reducers, small reducers. It's small not because the code is smaller, but because it will run on smaller amount of data than the reduced function. Remember, the reduced function gets data from all the mappers, right? I can transfer data to the same reducer from all the map functions, right? Depending on the keys that appear in that map function. But combine work on just one machine. So that's why it's small in terms of the data. You had a question? Oh, yes, shuffling will be done, of course, yes. Yes, because combine cannot do the whole thing. Across machines, no, yes. To do it across machines, you have to do the shuffling and the reduce will do it. Will do the work. Okay, so I think now you understand this last line. Used as an optimization to reduce network traffic. I don't think there is a problem with that, right? Okay.
How does MapReduce decide where to do shuffling?
Good question. But I think it's out of the scope of this lecture. Okay, so I think will we cover this? Maybe not, but it is definitely in the book. Okay. Okay. Here is the big picture now. So earlier we saw only map and reduce, right? Here we have combine and partition. So combine takes the output of the map, but after grouping, and produce something that is similar to the output of the map, and it has to be. That's a condition. These two has to be exactly the same types. Why is that? Because we might skip combine at all, right? Or run it. So the input has to be of the same type of the output, so that it can bypass combine if it needs to, and with no problem in the logic itself with the final output. Final output will be the same. Okay, so you cannot change the types here. That's a big difference between combine and reduce. I don't show reduce here, by the way. I don't think that reduce is gone. Reduce is there, but it's not on the slide. Okay. Yes. No. Both are options. You can do any of them. They are not dependent. So you can use partition without combine.
But partition cannot be denied by MapReduce.
No, it cannot be denied. It cannot be denied. Yes, because that's what you want. That's what you want. You want it that way. It will not control you that way. But combine is optional. Yes. You had a question? Yes. Okay. So partition. Can anyone explain it? Partition. What do you mean?
So the one we use partition.
Yes.
To assign for which reducer.
Yes, so we assign, partition determines which reducer will handle which key. Okay?
And why it's before shuffling? I was assuming it will be after, before reducer.
Oh no, because, okay, in shuffling, you need to shuffle, you need to move the keys to specific machine. So which machine? You cannot do that after you move it. You have to do it before, right? so that you know where to move the data. Yes. It's input and output based on the function as it's drawn now. For example, here, this is the input, this is the output of the map function. This is, but here there is a process here that is not that is not shown, which is grouping. Not shuffling. There is a local grouping that happens between map and combine. Okay, let me say it again. You see here the output K2 and V2, right? Okay. If you skip combine and partition, it's fine. It will be just this will be input to shuffling, right? As usual. Now, combine, try to aggregate locally the values that are associated with the same key. So we have to do some local grouping first. It's not shown here, but it's shown in that sense that this one will be transferred to be like that. This one? Sorry, this one? No, this is the input to combine. Okay.
After grouping.
After grouping, yes. Let's look at it here.
So if combining, it was supposed to combine output from different mappers, right?
From different mappers on the same machine.
On the same machine.
Yes. So, Reem, we produced here Clinton. Okay? Right? Now, what happens with the combine? If combine will run here, before it runs, the input to it will not be 3 records. It will be just one value, which is for Clinton specifically, not for everyone. But for Clinton, for example, it won't be Clinton and then this, what is this? What's it called? The green document, and then Clinton and green, and then Clinton and red. No, it will be one Clinton, because there will be grouping here, not shuffling, by the way, not in the shuffling, but I don't have space. It doesn't look nice, but forget about that. The shuffling is here, okay? So Clinton and this green thing twice, and the red thing. That will be the input to the combine function. It's a small reducer, Reem. What is the input to the reducer? Always the input to the reducer is one key and the list of values, right? So this one also takes one key and list of values. From where? From the output of the map functions that are on the same machine. You got it now? It's like, I hope. Yes? No, the grouping is done before calling the combiner. Okay? Okay, any other questions? So let's get back to here. So takes key and a list of values and produce list of key and value pairs. Exactly as the output of the map function. I mean in terms of structure. Okay? And then the partitioning, then the shuffling, and then the reduce. Two more details. Oh, here? Oh no, we just ignore. It's a bit tight here. It's a bit tight here. Yeah. But it's clear that this is the input, this is output, this is input, this is output, and this is also output. But and we ignored here the reduce. Now, two more details. There is a barrier between the map and the reduce phases. What does that mean? If you remember the word barrier, it means that we have to do some synchronization. We have to wait. We have to align time between different workers. So there is a barrier between map and reduce phases. That means that we have to wait for all mappers to finish before we can start the reduce phase. Why is that? Let's get back to the basic slide, this one. Reduce cannot start until all map function finishes. Yes. Because of the shuffling. Why? Because we need all the values before the reduce can start. We need all the values that are associated with the same key before the reduce starts. We cannot make sure that this is the final list until the last mapper finishes processing of the last record. We cannot start because maybe the reduce function needs all of them before it does anything. Okay, so we cannot start the reduce function, the reduce phase, except when until the map function finishes. That's what we mean by barrier. There is a barrier here. Okay, there is like a wall between them. Okay, map has to finish before reduce can start. But I think this is written. If we disable the shuffling ده احنا بهدلنا خلاص it's no longer MapReduce. Okay. Sometimes what? Okay, we'll get to that. Okay, we'll get to that. Actually, let me answer it now, but in maybe a couple of minutes. We'll finish very soon. Okay. We said that there is a barrier. Okay, but we can start copying. Yani moving the data across the network can start. Yani once one mapper finishes, its data can be distributed over the reducers. But we cannot start the reduce function itself, the execution of the reduce function, unless everything finishes. And that answers your question, Reem. Because in these interfaces, they consider this copying part of the reduce phase. Okay? But you understand now that what we mean here is that the call of the execution of the reduced function cannot start anywhere until the last mapper finishes. Because the last mapper might produce something for my key. I have to wait. We never know. We cannot anticipate. Okay? Is that clear? That's the first one. The second one, keys arrive at each reducer in sorted order. Now we mentioned that multiple mappers can, of course, one mapper can, of course, process multiple records, right? Same for the reducer, of course. One reducer, machine, one worker, can reduce multiple keys, right? Because the number of intermediate keys can be much more than the number of actual workers, reducers. And that's why the partition function will help us to assign. So that means that one reducer can actually process, of course, sequentially, a number of keys. Okay? This says that what will happen actually is that these keys will be sorted, and that's a side effect of how shuffling works. Okay? So it will be just like that with that implementation, that the keys that will be processed by the same reducer will be processed in sorted order by keys. Okay, so the keys will be sorted. But across reducers, of course, there's no order. Okay? Okay, خلاص, inshallah, we'll stop here and continue next time. Assalamu alaikum wa rahmatullahi wa barakatuh.